In the past decade, scientists came up with a plan to drill a 6-mile deep well. Sounds ordinary enough. Haven't we already drilled a lot of them? Like thousands? But this time, the drill wasn't meant for a desert or the ocean floor or an oil field. People wanted to do it inside the Yellowstone supervolcano. Yes, that very place where one of the planet's most dangerous forces lies dormant underground. A force capable of covering a whole continent in ash, plunging Earth into a volcanic winter and wiping an entire region off the map. If something goes wrong, the caldera could collapse. Ash could blanket the skies over America, crops would die, and acid rain might reach other continents. Some say this project is essential for humanity. Others fear a disaster straight out of a movie. So what's really going on there, and why? Let's find out. Ancient threat. The Yellowstone volcano is one of those things on Earth that you read about in scientific articles and then sit there for a couple of seconds thinking, wait, that actually exists? It's not just a volcano, it's a supervolcano, and it lives right under one of the most famous national parks in the U.S. It's a place where tourists stroll among geysers, taking selfies by boiling hot springs, and have no idea they're standing on the lid of a gigantic magma chamber. Beneath the park lies a vast underground system. Magma moves there like blood through veins. It heats the water, makes the ground rise and breathe. On the surface, it all looks mesmerizing. Clouds of steam, rainbow-colored pools, geysers breathing in rhythm, but all this beauty is just the heartbeat of something that once changed the face of Earth. Scientists have been watching Yellowstone for decades. GPS stations record tiny uplifts and subsidence of the ground. Sensors catch the chemical composition of gases. It helps them see how deep the magma is stirring. Satellites scan the park around the clock, and somewhere underground, tens of miles deep, there's silence that hundreds of experts from all over the world are listening to. Why all the fuss? Because Yellowstone has already erupted 3 times, and each time it changed the climate of the whole planet. The last one happened 640,000 years ago. If it happened again, North America would literally disappear under a layer of ash. Thousands of miles around would turn into a dead plain. The sun would fade behind a shroud of dust. Temperatures would drop, crops would die, and Earth would hit the reset button. It's hard for people to accept that under their feet lives a force capable of rewriting everything, and yet it quietly exists, pretending nothing bad ever happened or will happen. We're used to the idea that if something can be dangerous, we must control it. But here, we can't. We only watch, measure, observe, analyze. And thanks to that, we know there are no signs of critical changes building up, no accelerated inflation of the crust, no alarming something suddenly shifting inside signals. For tens of thousands of years, Earth's been calm. Yellowstone is in a dormant mode. It's alive, but not aggressive. That's why scientists keep repeating the chance of a super eruption anytime soon is extremely low. Not just low, it's so low that statistically, humanity is far more likely to live through dozens of global crises, and Yellowstone would still be just a beautiful park with geysers. If you put it in numbers, the odds are about 1 in 730,000. Experts even say we're more likely to get hit by an asteroid that wipes out civilization. So should we stop worrying about the volcano? Nope. That logic only works as long as nobody messes with it. But humans wouldn't be humans if they didn't try to sneak into the heart of a burning mountain, and that's where things start to get interesting. Light from a volcano. There are ideas that first make you laugh, and then you just sit there for a few minutes staring into space thinking, only NASA could come up with something like this. And one day, they really did. A concept to harvest energy straight from the Yellowstone volcano. Energy that doesn't depend on the sun, the wind, or any kind of fuel. It's basically endless on the scale of human civilization. Beneath Yellowstone lies infernal heat, and humanity has already learned to harness the warmth of the Earth. There are geothermal plants where the planet itself works as a generator. Why not, said NASA, except there's one problem. The heat isn't on the surface. You still have to reach it. So the plan was born to drill a well about 6 miles deep, straight into the zone where Yellowstone's heat could be tapped. The easiest way would be to start right above the magma dome, where all that heat is stored. But that's exactly what you shouldn't do. The top of Yellowstone is covered by a dense but brittle layer of rock, a kind of lid, and if you drill through it directly, decompression will happen. A sudden drop in pressure inside the chamber could cause gases to expand instantly and trigger an eruption. Even if you somehow avoid a catastrophe, another risk remains. the lid would become even weaker, and any tectonic movement could destroy it. That wouldn't bring the end right away, but it would definitely bring it closer. So yeah, not exactly the kind of plan people would approve. That's why NASA came up with a different approach. If you can't go from above, go from the side. According to the plan, drilling would begin outside the national park, and then a 6-mile deep well would angle down toward the side of the magma reservoir. That's where engineering takes over. You'd need ultra-heat-resistant drill rigs, metal cooling systems, pressure control circuits, and a dedicated surface infrastructure. Control, that's the key word here. The pipes would have to be sealed perfectly so the volcano doesn't eat through the casing, and the team would need to constantly monitor mineralization, temperature, and density. This project is an all-out engineering siege, and one mistake could mean disaster. After that comes the energy extraction. Cold water's pumped down the well under enormous pressure. It sinks deep into the network of hot cracks where the earth is already boiling. Down there, the water doesn't just evaporate into light steam, it reaches supercritical states, when it's no longer water or steam, but something in between, dense with energy, heated up to around 752 degrees Fahrenheit and under immense pressure. This is no longer kitchen-level physics of a kettle on the stove, this is industrial physics of high temperatures. Then all this thermal treasure rises back to the surface, and up there all that heat turns into electricity through turbines. Almost like in a regular power plant, only here the furnace is deep under your feet. The turbines spin, the energy flows into the grid, and in large amounts. Right now, scientists say that Yellowstone's surface heat flow equals about 6 gigawatts of thermal energy. If you take into account the losses that happen when converting it to electricity, you roughly get somewhere between 0.6 and 1.2 gigawatts of usable power. To put it simply, 1 gigawatt is about half the output of a typical nuclear power plant, or enough electricity for 700 to 800,000 homes. In short, Yellowstone could become the main energy source for many nearby towns. What's important is that NASA wanted to use this whole scheme not only for power, they wanted to gradually cool down the supervolcano. The idea wasn't just take the heat and turn it into electricity, but rather take it so consistently that the volcano cools faster than it heats up from the inside. And that's pretty straightforward logic. To put it simply, if you were constantly taking heat away from a pot, it'd cool down. Only here, instead of a pot, you've got a giant magma reservoir beneath Yellowstone. The only difference is scale. If we skip the fancy science talk, the cooling would look like this. Hot energy in the form of heated water or steam would be constantly extracted from the depths. That energy wouldn't stay in the volcanic system, it would flow into turbines, into electricity, into city grids. In other words, NASA literally planned to slowly pump out the volcano's inner heat to the outside. Naturally, many people immediately wondered, how much is all this going to cost? The project clearly didn't look like something easy or cheap. NASA's answer was about $3.5 billion for the whole thing. By the agency's standards, that's not much. For that money, they could get both energy and a gradual cooling of the most dangerous volcano on Earth. But then it turned out that money was the least of the problems. Huge nuances. It all seems under control. If you drill carefully and stick to precise calculations and ultra-sensitive equipment, nothing should happen, especially since a borehole is just a thin tube going deep underground. But Yellowstone has its own history, and it shows that even being careful doesn't really work here. In 1929 and 1930, and then again in 1967 and 1968, USGS scientists tried drilling very shallow holes, no deeper than 1,080 feet. The goal was purely scientific, to understand how the hydrothermal system works. But as soon as the drill string reached a layer of superheated water, things spun out of control. The wells began shooting out steam, boiling water, and even rocks. One of the researchers later called it a shattering experience. Even though they drilled far from the main geyser fields, many nearby hot springs changed temperature and activity. One of the scientific wells left open rusted over the decades and started spewing boiling water again. It happened in 1992. So when people say drilling in Yellowstone is safe, always remember, even a few hundred feet were enough for nature to strike back. Now imagine a well 6 miles deep. Even if the drill doesn't reach the magma, the danger doesn't go away, because the very act of drilling interferes with a system that's been in balance for centuries. You're cutting into a network where everything is connected. Pressure, steam, hot rock. And any new opening can shift that balance. Heat might start escaping in new directions. Water might move through different cracks. pressure might change in unexpected places. At first glance, it seems harmless, just a borehole, just heat exchange. But Yellowstone isn't just a place, it's a vast living mechanism. Cool one part of it, and it reacts somewhere else. A tiny crack might appear or a slight shift that triggers a chain of new movements. All this can happen without any eruptions or lava, just a slow-growing instability underground. Even without an eruption, drilling could open up channels for gases to escape. Where pressure and temperature once kept them sealed, a new crack appears, a new path to the surface. Hydrogen sulfide, sulfur dioxide, carbon dioxide, all of it could burst out from the depths along with steam. Not as a doomsday cloud, but as a slow, steady breath of toxic fumes. And yes, let's not forget that one of NASA's goals here is to cool down the volcano and thus save us from catastrophe. To trigger the very thing you're trying to prevent doesn't sound too appealing. Still, even without any disasters, this clever project wasn't exactly a recipe for success. On paper, it's simple. Water flow, cycles, geothermal reactors, all working slowly and steadily, cooling the system over the years. But when scientists tried to estimate the actual scale of thermal energy under Yellowstone, it turned out to be like trying to cool an ocean through a straw. The magma chamber is enormous, and to truly lower the risk of a super eruption, it would need to be cooled, not a little, but by roughly 1/3. This isn't about decades or centuries. It'll take thousands of years of continuous heat extraction. Thousands of years without interruptions, equipment failures, changes of civilization, shifts in politics or budgets. Almost an eternity by human standards. During that time, the country that started the project could disappear. Cities could vanish. The technologies that began it could be long gone. But for the technologies to disappear, they should be developed first. At this point, there are no technologies capable of drilling a 6-mile deep well in Yellowstone conditions. Sure, people have drilled deep before, 5.6 miles in Germany, 7.5 miles in Russia. Yes, it was deep and hot there too, but those were different environments, different temperatures, different chemical conditions. No one was trying to approach the magma of a supervolcano. Yellowstone's an aggressive, chemically saturated, ultra-hot environment. It's not just hot, it's a mix of pressure, superheated fluids, acid gases, corrosion, and unstable rock. Steel, cement, electronics, everything dies there much faster than we're used to. And that's not theory. Even at 1.2 miles deep in Iceland, where they tried to reach a superheated steam zone, equipment and materials failed quickly. Now imagine 6 miles and not just one day of work, but 1,000 years of it. And then there's the water issue. NASA's design called for a closed-loop system. In theory, part of the water would circulate back through the pipes, like coolant in a radiator, but in reality, under such temperatures and pressures, some of the water inevitably gets lost, seeping into rocks, evaporating, escaping through microcracks, or reacting chemically with minerals. So engineers assumed they'd need to constantly add more water to maintain pressure and temperature in the system. That means a continuous draw on outside resources, hundreds of thousands of cubic feet every year. And that's one of the weak spots of the concept. Yellowstone sits in an arid mountain region where every drop of water counts. To cool the volcano, you'd basically have to feed it with rivers, pumping them into the earth. And just when you think there are already more than enough reasons to abandon the idea, there's the final one. We're talking about a U.S. national park, a place where any interference is forbidden by law. Animals in danger. Yellowstone isn't just a spot on the map, it's a living organism, one where humans shouldn't step in with tools meant to fix the planet. Here, fragility and resilience exist side by side, and any attempt to interfere with its underground machinery, especially something as rough and long-term as drilling a 6-mile channel to release heat, isn't an engineering task, it's an ethical one. Because this isn't a desert or a testing ground, it's a national park, where every form of life has its place, and where we have no right to act in our own interests. Unless, of course, we're talking about a catastrophe. Grizzlies live here, a species that took decades to recover. Every adult grizzly is a slow biological investment. They breed rarely. Not all cubs survive, and their territories are vast. Wolves are another story. They were brought back here in 1995, and that experiment became one of the most famous examples of a trophic cascade. Where a predator returns, the behavior of herbivores changes, vegetation recovers, and the diversity of birds and small animals comes back. People literally watched how the presence of one species reshaped the course of a river. Now imagine what would happen if we started reshaping the thermal foundation of the entire region. Bison are the symbol of the park. This is their genetic heart. They're not decorative zoo bulls. More than 5,000 roam here freely, living like true wild animals, not museum pieces. There's also the lynx, one of the most elusive and rare predators in North America, and the wolverine, a one-of-a-kind creature that needs enormous hunting grounds. And all of them live here not because humans created the right conditions. They're here because we decided not to interfere. The park's also home to over 300 bird species, including eagles, pelicans, owls, and sandpipers. Their migration routes stretch for thousands of miles. They depend on food that appears in specific places at specific times, change the chemistry of a spring or the temperature of a creek, and the whole chain can collapse. And Yellowstone's most underrated treasure are microbes, the same ones that live in boiling acid pools. They can survive in temperatures up to 194 degrees Fahrenheit, and they're the reason humanity developed PCR, the technology behind modern molecular biology. These organisms are like a library of future discoveries. If we disrupt the park's thermal balance, we could lose species that haven't even been described yet. That's why any massive engineering operation inside such a place isn't safe cooling. It's the risk of wiping out an ecosystem we don't even fully understand and losing what can never be restored. It's no coincidence that drilling of any kind, except scientific, is banned in Yellowstone. Since 1970, there's been a federal ban on commercial drilling across all national parks, including Yellowstone, and even the surrounding areas are off limits, because any drilling nearby can disturb the park's hydrothermal features. So we've got strict legal bans, countless potential problems NASA's plan could cause, and its overall inefficiency. It's clear why no one ever started work on that 6-mile borehole. Still, it might just be a matter of time, because recently, people have begun drilling into a supervolcano right next to a bustling city with hundreds of thousands of residents. A project on the edge of insanity. The Phlegrean Fields is a supervolcano with a caldera lying hidden right under the suburbs of Naples. Unlike Yellowstone, it's not in the middle of the wild. It's surrounded by cities, schools, roads, people. It's one of the most dangerous volcanic systems in Europe. Beneath it lie massive amounts of heat, gas, and molten rock that have been teetering on the edge for thousands of years. The volcano's history is a chain of powerful explosive eruptions, one of which, about 39,000 years ago, was so violent it may have even caused climate changes across Europe. And if a supervolcano like this were to erupt again, it would mean a global catastrophe. Columns of ash, gas emissions, collapsing roofs, grounded flights, acid rains, dying vegetation, the evacuation of millions. Everyone living around this supervolcano knows they're sitting above a ticking disaster that's better left undisturbed. That's clearly the last thing you'd want to do. Yet scientists actually decided to disturb it through drilling. An international project was launched, funded, and officially approved. Its main goal was to reach the zones where volcanic activity takes place. In other words, the experts wanted to get to know the volcano up close and personal. According to the plan, the well was supposed to go 2.5 miles deep, and what's most surprising is that these plans actually went from paper to real life. Yes, people really started drilling into a supervolcano. And as soon as the drilling began, the public exploded, because to the average person, it all sounded the same. Volcano plus drilling equals messing with a force you can't control. People in Naples and nearby towns started to panic. The media fanned the flames with headlines like "Scientists drilling into a supervolcano" and "Could they wake it up?" It even turned into a political issue, so much so that the project was slowed down under public pressure. Even within the scientific community, many began saying the risks of interference might outweigh the potential scientific benefits. In the end, they didn't reach 2.5 miles. They drilled a pilot well about 1,644 to 1,660 feet deep. Even so, that was enough for scientists to extract rock samples, install sensors, and gather valuable data about the geological structure and history of the caldera, as well as how it deforms. And if Italy really went ahead and drilled a supervolcano, then why couldn't the same happen in the US? Even in Yellowstone, despite all the enormous danger. The Italians could certainly offer a few tips on how to drill under extreme and dangerous conditions, and there's another country out there that's been carrying out risky drilling projects for years and has plenty of experience to share. The capital of extreme drilling. Iceland is a country that literally sits on a fault line. This is where two giant tectonic plates meet, the North American and the Eurasian. They're moving apart, and the Earth's crust is constantly stretching. And when something spreads apart, something inevitably rises from below. That's how magma, hot, fresh, young, breaks through to the surface more often here than almost anywhere else on the planet. Volcanism here isn't a rare event, it's the normal state of the environment. And that's not a metaphor, it's geology happening in real time. Iceland is one of the few places on Earth where you can physically see young Earth's crust almost live. New rocks form here literally within a decade. Rivers of lava and new vents aren't ancient legends here, they're news stories that happen within one generation. Lava periodically surfaces, gases erupt, the ground cracks open. This isn't exotic, it's the pulse of the country. People are used to living with it. They build towns next to old eruption zones. They know that the ground here isn't a stone wall, it's something alive. And that's what matters most when we talk about a potential cooling or energy extraction project in Yellowstone. Iceland knows how to work with the volcanism it has in abundance and in extremely risky conditions. There's a project called IDDP-1 created by Iceland to look straight into the heart of its geothermal engine. The first well was drilled in 2009 near Krefla. The plan was ambitious, to reach depths where the temperature is above 752 degrees Fahrenheit, where water turns into a supercritical state. But things didn't go as planned. At a depth of about 1.2 miles, the drills suddenly hit magma, real magma, for the first time in history. No one had expected that. The temperature, around 1652 degrees Fahrenheit. The pressure, off the charts. Any equipment just melted. The well had to be quickly stabilized, cooled, and turned into an experiment. When they pumped water into it, it instantly turned into steam hotter than 842 degrees Fahrenheit. It became the hottest geothermal well on Earth. They called it a lucky accident. And even that accident generated nearly 36 megawatts of power. The thing is, no one expected magma at just 1.2 miles deep, which means if the American project by NASA ever begins, something completely unplanned might happen there too. After that came the second stage, IDDP-2. In 2016, the drill rig was moved southwest to the Reykjanes Peninsula. Here, the continental plates literally split under your feet, and underground heat is even closer. The goal was to reach around 3 miles deep and tap into a stable supercritical zone. By 2017, the drilling had almost reached its target. The temperature about 800 degrees Fahrenheit, pressure 340 bar. That's not just hot rock, it's practically a living energy chamber. At such temperatures, any equipment simply burns out. Metals lose their strength, drilling fluids boil, threads disintegrate. Every foot deeper demanded new solutions, new alloys, coatings, cooling systems. But those very challenges made the project unique. For the first time, people got close to harnessing heat that comes directly from magma and proved that it's possible to work with it, at least for a few hours, without blowing up the planet. And Iceland didn't stop there. A new project recently appeared called Krefla Magma Testbed, or KMT. It's a natural successor to the IDDP-1 drilling project. Back then, they reached magma by accident. But that moment turned out to be the most valuable. It showed that magmatic contact can actually be maintained and that a well can exist next to molten rock without being immediately destroyed. Everything that used to raise doubts is now becoming a proper engineering task under KMT. All the lessons from IDDP-1, from materials and rock behavior to fluids at extreme temperatures, are now treated as the foundation, not as a lucky accident. The KMT project at Krefla will intentionally enter the magma system. The site was chosen where magma is actually reachable at depths manageable for the budget and where it's possible to build the infrastructure for long-term monitoring. The main goal isn't just to reach magma, but to turn it into a systematic research object, to find out which metals can survive, how to budget correctly, and how heat flow changes over long timescales. It's also important to figure out how to install new kinds of sensors and design the next generation of geothermal wells, magma-compatible ones. Iceland proves that even what once seemed impossible can actually be done. Still, that doesn't mean something like NASA's plan will ever go forward. Yellowstone supervolcano is a completely different case, with a completely different threat level.